went through, if you haven't seen it, and I made a formula sheet of all the formulas I had talked about last week, and we worked problems. For the most part, all of your problems from chapter 2 are pretty straightforward. As long as you know the formula, you just plug in what you have, solve for what you don't. There are, of course, some exceptions to that, and that's what we're going to do today. So the only thing I didn't do any examples of on Friday was the de Broglie wavelength. So I know that it doesn't look like that says de Broglie, but that is how you pronounce it. Anytime you're supposed to use this equation, it's going to say somewhere in the problem something about de Broglie. Otherwise, you could use several other equations that we've talked about, okay? So this is the only one where we are considering mass and velocity. And mass needs to be in kilograms, velocity meter per second. So let's just do a basic one, then I'll show you how it could get more complicated. So these are not in your textbook. I'm picking these out of a different text so that you'll have more practice problems in your text, basically. While y'all are writing that, don't forget our test is next Monday. I sent out the when everybody's going to take it, so make sure you double check that, triple check it, so you know when you're supposed to be here. Some of your names were highlighted. The only reason they were highlighted is because you were not here to tell me what time worked best for you, so I just put you in your normal class time. All right, one other thing I've mentioned several times. Anytime we use these equations, wavelength is always going to be needs to be in meters, or you're going to get it when you solve for it, it's in meters. But it's more convenient to express wavelength in nanometers. So a lot of times you're going to have to do that conversion either at the beginning or at the end. So in our case, we're going to solve for wavelength. This should have said estimate the Broglie wavelength in nanometers of a proton moving at 2.9 times 10 to the 8 meter per second, and then they gave you the mass of a proton. So this problem, everything that we're going to plug in is already in the units we need it to be in. So all we have to do is substitute in what we're given in our constant. Remember, H is a constant. It's Planck's constant. And I will give you H and C, the speed of light, on your exam. So you don't have to remember those. Though you'll probably know them by that time because you'll use them so much. All right, so let's plug in. H on top. Mass. Okay, so let's all enter this in on our calculator to make sure that we are entering it in correctly. That's a lot of exponents to deal with. And I'll talk to you about units in just a second. So y'all see if y'all can get what I got. If nobody gets what I got, maybe I did something wrong. Yes. Okay. All right, this is how I would enter it in my calculator, and I'll redo it to make sure. All right, first off, the times 10 to some power, I'm not sure if y'all know this, but you can simplify that with the E button. And then it just pops in as an E on your calculator. You can't find that button. Come see me after class, and I'll find it. All right, so put this first one in parentheses, then divide, do big parentheses, then small times small, big. again.
Would you count off like minus 1.33?
I know. You're somewhere close to my number. Yes. So, the reason mass has to be in kilograms, velocity has to be in meter per second, is because by definition, a joule is defined as 1 kilogram times meter squared over second squared. So instead of you having to remember this, I mean, of course you can if you want to, but if you just remember this needs to be in kilograms, this meter per second, then know that your wavelength will always be in meters. Okay, I'll show you how it cancels though. Let me come down here and do that. All right, so if my units are joule, I'm going to plug in kilogram times meter squared over second squared. So that's just taking care of the joule. Then I have times second. That's that. Then on the bottom, I have kilogram times meter over second. This second cancels one of these. Then this meter per second cancels one of these meters, and then this final second, then your kilogram cancel. Only thing you're left with is meter. But again, you don't have to remember this. As long as you remember kilogram, meter per second. Okay. All right, we got to take it one step further because it wants our wavelength in nanometers. So all we need to do is come right here. 1 meter is 1 times 10 to the 9th nanometer. I left my answer in my calculator. You just get 1.37 times 10 to the negative 6 nanometers. Okay, so this is a straightforward, all you got to do is plug in, you get your Broglie wavelength. Let's look at another one where it's not so straightforward. Okay, so this one, we're asked to define the Broglie wavelength, but we're given our mass in gram and then our velocity in mile per hour. So, do some conversions. First, mass. You could do this without setting it up like I'm about to, but I prefer just showing you like this. All I need to do is take gram to kilogram. So I know that 1 kilogram has 1,000 grams. So I'm going to divide 10.2 by 1,000. That's just going to move my decimal to places to the left. Okay. So you could have just moved your decimal if you knew that, or you could have done this. Velocity. What's going to require some work. I'm going to write that as this. 3.51 miles on top per hour, so hour on bottom. I need to get this to meter per second. They told you that 1 mile is 1.6 kilometers, so we can get mile to kilometer easily. So let's go ahead and do that. If I want mile to cancel, I'll put the 1 mile on bottom. 1.61 kilometer on top. So my mile cancel. Kilometer to meter, it's the same conversion as this. Okay, 1 kilometer has 1,000 meters. I just flipped it because I want kilometers to cancel. Yep.
I'm confused as to like I put 1,000 kilometers, that's on 1 meter. That's not that. Okay, but like how do you know where?
Okay, so think about it. 1 kilometer is very large. Okay, so you should have more meters than you do kilometers. So the 1 kilometer goes there, 1,000 meters goes there. Does that make sense?
The bottom one is supposed to come.
It just depends. So in this case, I wanted kilometers to cancel, so I just put kilometers bottom. Here, I wanted to be left with kilogram, so I put that on top, grams on bottom to cancel gram. And if you're still unsure about these conversions, your metric conversions, what I would do is I would go through and write out what conversion factors you want to use every single time. Memorize them, use them the rest of the semester. So like 1 liter or one any base unit has 1,000 milliliters or grams. 1 gram, 1,000 milligrams. 1 kilogram, kilometer, whatever, has 1,000 grams or whatever your base unit is. I just go through and make me a list. All right, so here we have now the unit we want on top. We don't have the unit we want on bottom. So it's up to you if you want to stop here, go ahead and solve, and then go back and do your hour. I prefer to do it all in one step, but again, that's up to you. Okay, so I'm trying to get to seconds. Well, I know, okay, first off, I want hour to cancel on bottom, so hour goes here. If you don't know how many seconds are an hour, you do know how many minutes are an hour. So 1 minute has how many minutes? 1 hour has how many minutes? Yes, 60 minutes. Okay, and then so hours would cancel. So now I have minutes. Well, I know that 1 minute has how many seconds? A minute cancels. So I'm left with second on bottom and meter on top. So now go through, multiply everything on bottom, divide by everything. I should not talk. Multiply everything on top, divide by everything on bottom. At 1.57 meter per second. Okay, now we've converted both mass and velocity. Now we go actually plug it into the formula. So here is kind of a tip. On your test, you only have 50 minutes to take your test, okay? So I'm essentially testing you on 3 chapters. The Essentials chapter, Chapter 1, Chapter 2. Well, to save time, I can test you on the Essentials chapter by just asking you this question. It tests your conversion knowledge and your Chapter 2 knowledge. So that way, we're not running out of time. So be mindful of that as you're studying, okay? It all just kind of builds on each other. All right, so let's plug it in. 626 times 10 to the negative 34 joule times second over mass in kilograms, velocity in meter per second. Plug it in. Your calculator. And again, I just know that I always get my wavelength in meters from this equation. You all get 4.14 times 10 to the negative 33 meters. But the problem asked for centimeters.
I got it to the negative 34.
Oh yeah, that's where I messed up. Yeah, so what y'all got should be correct. Yeah, negative 32. Now we gotta take it to centimeters. How many centimeters are in a meter? Yep, 1 meter has 100 centimeters. It's not gonna change my number very much. It just makes my exponent a little less. Negative 30. So chapter 2, basically, we had to learn about waves because we now know that electrons can behave like a particle and a wave. This equation is the only equation that relates the particle nature, so the mass and the velocity, and the wave nature of matter. So this number is so not nice. It's not on the electromagnetic spectrum because honeybees do not behave like waves and particles. Only electrons and photons do that. Okay, so that's really what we've conceptually covered up to this point. So I want to take a break from math for a minute and let's talk about quantum numbers. So there's two people I need to mention before we do that. Heisenberg, not the guy off Breaking Bad, and Schrodinger. All right, Heisenberg. More importantly, the Heisenberg uncertainty principle. I'm going to write this just in my own definition first. All right, so in layman terms, Heisenberg's uncertainty principle says that you cannot know the position and the momentum of a particle simultaneously. Basically, what that means is if you look for the position of a particle, then the momentum is undeterminable because you're trying to single out particle nature. So you can no longer look at its wave nature. If I want to know its momentum, I've kind of got to look at it as a wave so that I know how fast it's traveling. Well, if I'm looking at momentum, then I can no longer know its exact position. Okay, so that's what Heisenberg's uncertainty principle states. If you look in your notes, you'll see that there's a mathematical formula. You do not have to know that mathematical formula. As long as you know this, you'll be fine for your test. All right, so basically this leads to the fact that other words. All right, so for a normal object in classical physics, if you know its position and then the speed that it's going to leave that position, you can determine what path it'll take. So let me draw that as this. Classical physics. Back when particles were just particles and not waves. All right, well, subatomic particles, electrons, they don't behave like this. Instead, if they start here, because they're like a wave, they could end up anywhere here. We don't know. Okay? So, where Schrodinger comes in is that he says we can't really know where they're going to be. We can only know a good region of where we might find them. Okay? So or you'll see in your notes, dots represent the area that you could find that electron. Somewhere in this region. We don't know. Have you guys ever heard of Schrodinger's cat? Okay, so it's a thought experiment if you haven't heard of it. It's if you put this deadly gas in a box, and it's like set up like all these things have to happen in order for that gas to be released. Okay, we also put a cat in the box, close the box. The box is closed. So we don't know if the cat's dead or alive, okay? Because we're not looking at it. It's kind of the same thing here. Depends the closer you look at it, the less you really know, okay? That's quantum mechanics for you. So Schrodinger came up with an equation. You don't have to know, but I'll give it to you anyway. It involves a lot of calculus. His equation just allows us to calculate the probability of finding an electron, okay? So this funny H and this E's, those are operators, and these here are known as a wave function. But these wave functions have no physical meaning. I know, crazy. The wave function squared is the probability density Wave function squared is the probability density of finding an electron at a particular point in space. I know that this all sounds crazy, but it works. It's the best model we have to describe an atom and its electrons. So let's look at the models of the atoms that we've talked about in the last two chapters. All right, we started with J.J. Thomson's model. What did he call it? Yes, the plum pudding model. It's kind of like a chocolate chip cookie model also. These negative things are my electrons. They're also like chocolate chips. They're just dispersed in this atom random. Then came Rutherford. Rutherford introduced the nucleus to us. Okay, so all we knew then is there was a positive nucleus. There were electrons somewhere not in the nucleus, so somewhere around the nucleus. This chapter, we talked about Bohr briefly. I think it was on the second part of chapter 2. He said that electrons were in orbits around the nucleus. And they were at certain distances around the nucleus, and they're just orbiting around. Bohr's model. The last model and the most accurate is Schrodinger's model. There's a positive nucleus, we do know that. Okay. Electrons are somewhere in this shaded region. They're not orbiting the nucleus in a perfect circle. They're just somewhere out here in this area. This is the best probability that I can give you. This is what we know the atom to be now. So Schrodinger calls these atomic orbitals, and we're going to learn a lot about them. And that's very different from Bohr's orbits. Okay. So orbit is like the sun and the planets. Orbitals, we just have this idea of where those electrons are. Anywhere in this shaded space is the atomic orbital. Okay? And we're going to build on that model. Oh, I have 9 minutes. Good. I can at least start. All right, so there are There are 4 different type of orbitals that we'll consider in Gen Chem 1. If you're a chemistry major and you go on to advance in organic, you'll talk about others. That is way beyond our scope in Gen Chem 1. So if you look at my typed notes on page 10, there are all the different atomic orbital shapes. Okay, you don't have to know these. I just want you to see them because I think it'll help your quantum numbers make more sense. Okay, so I would look at those if I were you. So the rest of this chapter really just talks about the quantum numbers. There's 4. So in chapter 3, we're going to draw orbital diagrams for all the elements on the periodic table. Well, not all of them, but most of them. Here's an example of what an orbital diagram looks like. I'm introducing this because I think it helps quantum numbers make more sense. So there's 4 quantum numbers. The first 3 just describe the orbital that an electron is in. Okay? So 3, I'm going to abbreviate quantum numbers as QN. 3 quantum numbers. All right, so the first one, we abbreviate N. We call it N. It is the principal quantum number. All it tells me is what energy level that electron is in. So over here, I have them numbered and lettered. So it says 1s, 2s, 2p. This 2 and this 1, that tells me what energy level I'm in. Okay, so this is the first energy level, this is the second energy level. So that's all that the first quantum number does. It tells me the energy level. Second quantum number. We abbreviate with an L. And we call it the angular momentum. All this does is tells me the shapes of the orbital. So I promise you that we would rather just talk about the L quantum number as we would for you to have to look at all these different atomic orbitals and identify their shapes. And like have to remember, oh yeah, that's the px orbital, or that's the dxy orbital. It's real complicated. Then the last quantum number that describes the atomic orbital is the magnetic quantum number, and it's represented by the letter M with a subscript L. So M sub L is how you would say that, M sub L. The reason it's M sub L is it's describing your L quantum number, okay? So it's the orientation of the orbital. So your different shapes have different orientations. So the M sub L describes your L. So I will go in much more detail about these and post them for y'all. Okay. Yeah. Y'all come see me if you need me. Otherwise, keep doing what you're doing. Have a good week.